So recording is on. Okay, today's our energy education session. And I want to introduce Kai Landskron, our speaker. Is a professor at Lehigh University. He holds a PhD from the University of Munich in high pressure synthesis and crystal structure determination of phosphorus nitrides. He also conducted research in Toronto before joining Lehigh in 2006. Dr. Landskron's current research interests are in materials chemistry associated with energy and environmental applications related to climate change. He is interested in new materials and processes for carbon dioxide capture, energy storage, energy saving, which brings them to us today. Please join me in welcoming Dr. Landskron to the RF100 Energy Ed program. Thank you, Kai, for coming. You may proceed when ready. And I just wanted to remind the audience, you can enter questions in chat at any time, and we'll convey those to Kai at the end of his session. Thanks, Kai.
Thank you very much, Bill. So today I would like to talk about a new energy storage concept with which we want to achieve 100% renewable energy. So we know all that climate change is a big problem, and in order to mitigate climate change, we need to transition from fossil fuels to renewable energy, and we need to develop the technologies that are able to do that. So in order to make an informed decision what technology may be suitable, it is worthwhile to have a look at how carbon dioxide is actually being generated. So you see here on this slide how much CO2 is being produced by the different sectors. So you see that the dominant sectors are actually the transportation sector, followed by the electricity generation sector, followed by the industry sector, followed by the commercial and residential sector, as well as the agriculture sector. So any technology that would want to effectively mitigate the CO2 emissions would necessarily need to address most, if not all, of these sectors. Most importantly would be the biggest sectors, namely the transportation sector, as well as the electricity sector. So what hinders currently the transition to wind and solar powered society, as wind and solar are currently the most dominant renewable energies that we have at hand. At first glance, you may think, well, wind and solar energy is still more expensive than just burning fossil fuels. And that was actually true until recent years, but today it is not true anymore. Meanwhile, wind and solar energy is even cheaper than the burning of fossil fuels. So if the price of renewable electricity generation is not the problem, what is the problem then? And the problem is that wind and solar energy are intermittent forms of energy. So the wind doesn't blow at a constant rate, and the sun always doesn't shine always at the same power, and that creates instability in the power grid. And therefore, there is a need for the development of energy storage technologies that can actually store wind and solar energy when excess wind and solar energy is provided, and which can deliver wind and solar energy back into the grid when additional electricity is needed. That, however, would only address the electricity generation sector. It would not address the transportation sector, because solar and wind can also not directly power vehicles. So any energy storage technology should also be suitable for transportation applications. So what would be a good solution? So a good solution would be a universal energy storage concept that would be applicable for both the grid and the transportation sector, and potentially for the others as well. It would have to be economic, and it should have a low environmental impact with ideally no CO2 emissions. It should also not require a new infrastructure, so it should not be disruptive. So ideally, we would want to avoid to break down all our existing infrastructure that we currently have in order to provide ourselves with energy and establish a completely new one. It would be better if we could still use that existing infrastructure. And last but not least, it should be convenient and also safe to use for the consumer. When you deal with energy, there's always an inherent safety aspect to this, especially when you deal with a lot of energy, the potential danger scales accordingly. So we think we have a solution for this problem, and this solution is an energy storage concept, which is applicable to both grid storage and transportation applications. So let us first look at electrical grid storage. So we produce electricity using renewable energy sources such as wind and solar and power our homes with it. So in the case we have excess electricity, then we will use this excess electricity in order to convert a hydrogen-lean liquid hydrocarbon into a hydrogen-rich liquid hydrocarbon using a device which is called an electrolytic hydrogenator. So this device will use water as a hydrogen source, and with the help of the excess electrical energy, it will extract the hydrogen from the water and convert the hydrogen-lean hydrocarbon into a hydrogen-richer liquid hydrocarbon. And these forms of hydrocarbons can be stored conveniently in existing oil tanks, and we can use the existing hydrocarbon infrastructure in order to store that liquid hydrocarbon and also to distribute that liquid hydrocarbon to different places. So when we do not have enough energy generated from wind and solar, then we can use another device, which is called a dehydrogenated fuel cell, in order to do the opposite and convert the hydrogen-rich liquid hydrocarbon, which is also energy-rich, into a hydrogen-lean liquid hydrocarbon, thereby generating water. So with help of oxygen, we would extract some of the hydrogen, which is in the hydrocarbon, combine it with water, and thereby generating electricity. So in a similar way, we can also use this concept for transportation applications. So we can fill our hydrogen-rich liquid hydrocarbon into a conventional steel tank within a car. The only difference would be that the steel tank would have a diaphragm that would move as the energy-rich liquid hydrocarbon would be converted into the energy-poor liquid hydrocarbon. So this is actually shown here. So while the car drives, the liquid hydrocarbon would be pumped through the fuel cell. There it would be converted into the hydrogen-lean hydrocarbon and pumped back into the steel tank, whereby the diaphragm here would actually move. So eventually, the tank of the car would be filled completely with hydrogen poor liquid hydrocarbon. So in this case, the car could go to a conventional gas station, and at the conventional gas station, one could pump out the hydrogen poor hydrocarbon to the gas station, and from the gas station, hydrogen rich hydrocarbon could be pumped back into the car. And that could be done within a very short time frame, within a few minutes, just the way we are accustomed to it today. So over the time, the gas station would run out of, well, hydrogen-rich liquid hydrocarbon, and the storage tanks would be filled with hydrogen-lean hydrocarbon. So as this happens, new hydrogen-rich hydrocarbon could be transported by tanker truck to the gas station, just as it is done currently. Just that tanker truck would not have gasoline or diesel, but our hydrogen-rich liquid hydrocarbon. So at the same time, the tanker truck could actually pick up the hydrogen-lean hydrocarbon and transport it to a central regeneration facility. And at that central regeneration facility, that hydrogen-lean liquid could be converted back into the hydrogen-rich liquid using water and electricity. So this would be one way to do it. I wanted to point out that this is actually not the only way to do it. So it would be even possible that a gas station could have electrolyzer that could do the regeneration. And in addition, it would even be possible to regenerate the liquid within the car if the car had an electrolyzer in addition to the dehydrogenative fuel cell. So once your fuel is spent, you would actually plug in your car into a power outlet, and then with the help of electricity plus some water, your fuel would be regenerated within the car. And all these possibilities are not mutually exclusive. Okay, so now which liquid hydrocarbon would be the ideal fuel for that purpose? And our fuel of choice is a molecule which is called hydrodibenzyl toluene. You see the chemical structure here. So you see that this molecule has actually 3 6-membered carbon rings that are interconnected. And they are hydrogen atoms bonded via chemical carbon-hydrogen bonds to these 6-membered rings. And as the dehydrogenation occurs, that fuel, the hydrodibenzyl toluene, would be converted within the fuel cell into dibenzyl toluene, which would now have 18 hydrogens less. And this would be our hydrogen-lean fuel. So what makes the hydrodibenzyl toluene system so attractive? So first of all, this fuel pair comes with a very high energy density of approximately 1,578 watt-hours per liters. So the energy density is actually high enough so that your fuel tank in your vehicle would only need to be approximately 1.5 times greater in comparison to a fuel tank which would be run by gasoline. So another very desirable feature is that this liquid has a stability range between about -30 degrees Celsius and +300 degrees Celsius. So you can use it in pretty much all climate zones. And because it has such a high boiling point, it is also very little volatile. It is practically odorless. For that reason, it also has a very high flash point, so it's extremely hard to ignite. So for that reason, it has very good safety properties as well. It has a low viscosity, so it flows pretty easily, and it is also immiscible with water. And that is important with regard to its environmental profile. So in case of a spill, the fuel doesn't mix with water, and for that reason, it can be relatively easily removed from any water. Last but not least, this fuel is also cheap. So you can currently purchase it for $1 per kilogram at the multi-ton scale. It is already produced for a different application, namely as heat exchange fluid. So at first glance, this $1 per kilogram value may still sound a little expensive, but in comparison to diesel or to gasoline, but you have to consider here that we can regenerate that fuel multiple times, and our goal is to be able to regenerate it at least 1,000 times. Okay, so now how does our technology compare with other energy storage technologies? So in the transportation sector, meanwhile, a lot of electrical cars based on lithium-ion batteries are emerging. So in comparison to lithium-ion batteries, our fuel has a much higher energy density. So that means that it has a significant higher driving range associated with in comparison to lithium-ion batteries. And that's even the case when you factor in that a fuel cell only has approximately 60% efficiency versus a lithium-ion battery. So that means only about 60% of the energy in the fuel can actually be converted into electricity that goes to the wheels, whereas in a lithium-ion battery, it's approximately 90%. However, our fuel cell, as we plan to design it, will be a so-called high-temperature fuel cell. And a high-temperature fuel cell can use its waste heat quite efficiently. So that means that the remaining 40% can be used for something. So for example, for heating the passenger cabin or for cooling the passenger cabin. And factoring in these co-generation factors, we can potentially achieve a significantly higher efficiency in comparison to the 60% energy efficiency. So how does our technology compare to hydrogen gas technologies that use a conventional fuel cell, which is fed by hydrogen gas? So one major advantage is that we do not need a new infrastructure for the distribution and storage of our fuel, whereas in the case of gaseous hydrogen technology, you require a disruptive change of infrastructure, which is very costly and which is also very time consuming. So secondly, the safety aspects of our technology are significantly more attractive in comparison to technologies based on hydrogen gas, because hydrogen is a gas with a very low boiling point. It's flammable, and it can even produce explosive mixtures with air. So for that reason, significant safety precautions are required when you work with hydrogen gas, whereas in our technology, we will avoid hydrogen gas consequently. That makes transportation and storage much easier, and all safety features that need to be present are much less significant. So when you compare hydrogen gas with the energy, with our technology, then you see that they're actually comparable. So hydrogen gas is actually the fuel with the highest gravimetric energy density. However, because it's a gas, you need to compress it in order to achieve a reasonable volumetric energy density, and that requires a heavy-walled and heavy steel tank. So for that reason, based on volumetric energy density, our two technologies are actually pretty much comparable. You could also, in principle, think of liquefying hydrogen, but hydrogen has a very low boiling point, which makes it very difficult to handle the liquid hydrogen safely and also economically. Okay, so now let me briefly go into a little bit more technical detail and explain the principles of a fuel cell, which is the central part of the technology, and what we actually need to change about a conventional fuel cell in order to make it practical for our fuel. So you see here a photograph of a fuel cell as we have it in the lab, and you see that the fuel cell has a kind of a sandwich structure. There's something in between two metal plates. So these two metal plates are actually just the current collectors that collect the electricity that comes from the fuel cell and circles it around. So here in this diagram, you see the internal structure of the fuel cell. So basically, a fuel cell has two electrodes, an anode shown here and the cathode shown over there. And these two electrodes are separated by an electrolyte, which is typically a polymer electrolyte membranes. And what we do in a fuel cell is that we pass, or in a conventional fuel cell, that we pass the hydrogen along the anode, and we pass air containing oxygen along the cathode. So now what will happen to these gases? So the hydrogen will come in contact with the anode, and at the anode, the hydrogen-hydrogen bond will cleave in the dihydrogen molecule, and we will produce hydrogen plus ions, also just called protons, and electrons. So these electrons, they go into the electric circuit and produce the electrical current, and from the load, they then go into the cathode. So the protons generated here will migrate through the proton conducting membrane to the electrode, the other electrode, which is the cathode. So what will happen at the cathode? So the oxygen sweeps by, and this oxygen picks up electrons coming from the anode. And as that happens, it converts into so-called oxide anions, and then these oxide anions combine with two protons coming from the anode to form water, so that water is your only emission product. So what do we need to change in order to make this fuel cell practical for the HDBT fuel? Okay, so the HDBT fuel is different in many ways. So the HDB fuel is a much larger molecule, and we will not feed a gas into the fuel cell. We will actually feed a liquid into the fuel cell, and we have to redesign our fuel cell accordingly. So in order to understand what we need to do, we need to look a little bit closer into how a fuel cell is actually constructed. So you see again here the photo, and now you see a refined schematic for the interior of the fuel cell. So now here to the very outside, there are still the current collectors. Okay, so these are just these two metal plates here. And then these current collectors are connected to what is called flow channels for the fuel. Okay, in a conventional fuel cell, that would be hydrogen on the anode side and oxygen here on the cathode side. So you see actually here a photograph how these flow channels look like in reality. So typically they are engraved in a graphite plate. So you use graphite because graphite is electrically conducting and it doesn't easily corrode. So attached to the plate with the flow channels is then what is called the fuel diffusion layer and the air diffusion layer respectively. So these here are the green parts. Okay, so that is typically a carbon cloth, as is shown here in that photograph. So what we need to do is to basically optimize both the flow channels as well as the fuel diffusion layer for the HDBT molecule. We have relatively little to do here on the cathode side, because on the cathode side, we will still just flow oxygen through the fuel. So next, and most importantly, you have here so-called catalyst layers. Okay, we have one catalyst layer for the oxidation of the fuel, and we have one catalyst layer for the reduction of the oxygen. Again, we don't expect a lot of work to do on the oxygen side, because we will still use oxygen from air for the oxidation of our fuel. But on the anode side, we now have a significantly different problem, because we do not have hydrogen-hydrogen bonds to cleave, but we have carbon-hydrogen bonds to cleave. So within the catalyst layer, the actual chemistry will happen and the transformation of the fuel into the reaction products. Okay. So last but not least, we have here the H+ conducting membrane, and the photograph is shown here. And this proton conducting membrane looks basically like a sheet of plastic, but it's a very special sheet of plastic in the sense that it's able to conduct protons from the anode side to the cathode side. So now let us have a closer look at the catalyst layer for the fuel conversion reaction. Okay, so the fuel conversion actually takes place at the interface between this catalyst layer here and the proton conducting membrane. And that is because the electron coming from the hydrogen-hydrogen bond cleavage must actually hop into the electrically conducting catalyst, which is typically platinum, and the hydrogen must hop in form of the H+ ions into the membrane. Okay, and then the two electrons, which are in the hydrogen-hydrogen bond, can go from the platinum into the electrical circuit, and the two protons, they are moving through the membrane to the other electrode. So our job, and that's actually the most important job that we have to do, is to adjust the catalyst layer and the interface between the catalyst layer and the membrane for the perhydrodibenzyl toluene molecule, which is now carbon-hydrogen bonds and is significantly larger than the simple hydrogen molecule. So our task is to design a catalyst layer, which is able to do the following. We have to cleave our carbon-hydrogen bond, and we have to cleave it so that this electron here jumps to the catalyst material, and from there into the electrical circuit. And the hydrogen again forms H+ ions, which then goes into the membrane and moves to the cathode. So then we have actually cleaved only one carbon-hydrogen bond, and that process must happen repeatedly until all 18 carbon-hydrogen bonds are cleaved. And after that, our 18H DBT molecule is fully converted into the DBT molecule. So this is basically from the science perspective what we need to accomplish in order to make a key step forward in this technology. All right, so now back to the applications. We can envision other applications, but the two that I have mentioned. So on the transportation side, I believe we cannot only fuel passenger cars and trucks with this fuel. There are also possibilities to power trains and ships and possibly even airplanes. And then we have covered more or less the entire transportation sector. I think we can also make an impact on residential when we reutilize existing oil tanks, heating oil tanks for our technology. So instead of conventional heating oil, we can just fill HDBT in these oil tanks, and then in the basement we connect this tank with a fuel cell, and then that fuel cell will generate electricity and DBT, which would then be in a separate tank, and that DBT could then be regenerated using an electrolyzer in combination with electricity, excess electricity, which is generated by solar panels. So this way, you could power off-grid homes, and you could also power multiple apartment complexes, for example. With that, you can actually create little mini grids with which you can power then entire communities. So now the big question is, where do we stand with this technology? And we are still at the very beginning. So we got a small research grant from Lehigh University in order to purchase some equipment, materials, and supplies to set up the lab. And you see here the lab bench in my lab, where we are currently about to set up the equipment for this process. And you see here a few cells standing on the lab bench, but you see it's all not completely set up and interconnected. So in order to fully realize this technology, of course, we would need a lot more money. I think this is pretty obvious. So to this end, we plan to launch a crowdfunding campaign on Indiegogo pretty soon. And our hope would be that one of you listeners may be inclined to make a contribution to that. You can actually already support this project if you want. I actually have a research gifts account on my Lehigh University website, and this is actually the link to this. So if you want to consider to support that project, you can actually already do that. With that, I would like to thank a lot of people, actually. So a lot of people have contributed such far to this project. First and foremost, Guido Pes, who is a former industrial scientist at a product, now retired and now working with me in my lab. He's actually the father of this idea. I also thank my research fellow, David Roberts, for his contributions. And I also very much thank Sean Simonet, Bert Brown, and Tinku Kanwaka, who have meanwhile formed a company around this project, which will facilitate the technology transfer from the university into the real world. And last but not least, I would like to thank Ed Yarish. He's actually the one who connected us all together and has created a decentralized organization which is called YASI, that tries to bundle expertise for renewable energy technology projects. Last but not least, I would like to thank Jim and Eva Wiley, Tim Beckham and Bill Saby at the Sierra Club for giving me the opportunity to talk here. And there are many more people involved that have contributed, which would go beyond the scope to mention them here. So with this, I'm at the end of my talk, and I would be happy to answer any questions.
Thank you very much, Kai. Enlightening presentation, so thank you for this. I'm going to turn it over to Eva, who will read out the questions that she's received. We have about 20 minutes remaining in the session. Thank you again.
All right. Boy, did I learn a lot. Kai, if maybe some of these you touched on, but I think it would be helpful to go back over a little bit.
Sure.
Can you speak in general terms about the energy requirements to support the process itself? From how much energy is required to basically create the rich hydrogen that's able to use as another source of energy.
So you're talking about the energy required to make the fuel cell going, or the energy required to generate the fuel?
To generate them. Well, actually both, I think, would be interesting.
Both of them. Well, the fuel cell, once up to the temperature, will run itself. Okay, so the fuel cell generates electricity, but it also creates some heat. Okay, and that heat can be used in order to keep the fuel cell at its operational temperature. Okay, actually it will produce more heat than just to do that, and that heat can then be used for other purposes. For instance, for heating the passenger cabin or a car or a home, for instance. Then for the regeneration, I mean, bottom line, you have to provide the energy that you have generated. Okay, and that energy will come out of wind farms or solar farms in combination with water. But that energy will be excess energy. Okay, that has no use at the point that it's created. Okay, for that reason, that energy is not expensive. Okay, it's excess energy that we will use in order to generate the fuel.
Okay, thank you. There were also questions about if this concept works with creating ammonia, and later stripping the nitrogen to create hydrogen to be used as an energy source. Thinking about, the question came from Gary. He was thinking about long distance transport of solar energy.
Yeah, that's a different technology. So the ammonia technology is trying to store hydrogen in the form of ammonia. Okay, and ammonia is comparatively easy to transport and store in comparison to hydrogen gas. However, in my opinion, it's not as easy to transport and store in comparison to a liquid hydrocarbon. Okay, And so for that reason, I think a liquid hydrocarbon is actually preferable over ammonia as hydrogen storage medium. Mm-hmm. So ammonia is basically a competing technology with ours. It aims to store hydrogen gas in a different way. Ammonia also has the advantage, well, it's toxic. Have you ever smelled ammonia and you know it doesn't smell very good and you easily get a headache from it? Mm-hmm. When you have a non-volatile liquid hydrocarbon, then that's not the case. So our hydrocarbon has a consistency similar to vegetable oil. It flows like vegetable oil. When you open the bottle, it practically doesn't smell. It's very hard to ignite. So it's very convenient to use in comparison to hydrogen gas and also in comparison to ammonia.
Okay. A few practical questions from the crowd. I think it's fair to say we're problem solvers in the midst. Questions about how much space, how much capacity would be required in a car, for example, to support the examples that you envision. Also,
well, about
I was going to say another dimension of that question is what about converting a home heating system using the previous conversation that you mentioned. So those are kind of some of the practical questions that are coming up.
Yeah. So your gas tank would need to be about 1.5 times larger in comparison to conventional gas tank, achieving the same driving range, assuming your fuel is gasoline. So as far as the home storage goes, your conventional oil tank will have all the capacity you need. Okay, that's because you only need the energy of the liquid in that tank when the sun doesn't shine enough to provide you the electricity. Okay, and when you have excess electricity, you can always use that excess electricity in order to regenerate your liquid fuel. So for that reason, you don't need all that much liquid fuel. I mean, a conventional oil tank, heating oil tank, needs to last a year, right? And you convert all of the oil in that oil tank to form carbon dioxide and water. Okay, that's not the case with our technology. Okay, for that reason, a far smaller tank may actually be sufficient. So your space in the basement will certainly not be a problem.
Mm-hmm. Would you envision storage cells as well?
Sorry?
Would you envision storage cells as well, or would all the energy just be created at the time of its use in a home environment? Mm-hmm. Like
the energy in the liquid will only be used when your solar cells on your roof do not produce enough electricity. Okay, but when they produce more electricity than you need, then that electricity will be used to regenerate the liquid fuel in your basement.
Okay.
Okay, so you have this liquid as a buffer.
Mm-hmm. Yep.
It's a buffer system.
And it might be premature, but do you have a thought about the lifespan of the new hardware that's required, the new system that's required? Is it a 30-year investment, for example?
Yeah, that's a good question. So there are two factors associated with it. That's the lifetime of the fuel cell itself, mm-hmm. and that's the lifetime of the fuel. Okay, so there are limits to the regenerability in the sense how often you can actually recycle this. You won't be able to recycle it infinitely often. So our goal is that you can recycle it for 1,000 times before you basically have to throw it away. So another question is, what do you do with the fuel once you cannot recycle it anymore? And there are also options. So the first option is you still use it as a conventional fuel, and that means that you can just burn it. Okay, you will still have saved a lot of CO2 when you burn it after you have recycled it 1,000 times. 99% of the CO2 will be saved. The other possibility is to use it as a feedstock for other products that are petroleum based. Okay, so you can, for example, make plastics out of that.
Yeah.
Okay, so the spent fuel may also not necessarily be useless. So with regard to the lifetime of the fuel cell, that is also part of the research work. So conventional hydrogen fuel cell have a lifetime of about 5 to 10 years. And our goal would be, well, to create a fuel cell which has approximately the same lifetime. Of course, the longer the better. But our benchmark for now is the lifetime of a conventional hydrogen fuel cell.
Okay. I think there's two more questions here that are queued up, and then if there's any others. What is the next step in your kind of proof of concept pilot prototype phase? Are you, for example, are you planning to put it in an automobile? Are you planning to use it in a home?
Eventually, yes. But as visible from the photo of my lab that I showed,
Right.
we are still a little bit away from doing that. So we still have to work on lab scale fuel cells and show that these lab scale fuel cells have the performance and the stability
Right.
required. So and then you can begin to scale this and begin to try to incorporate the fuel cells into, for instance, vehicles.
Is that
and then see how they do in that application.
Okay. All right. And thank you. And the last question is, are you aware of other groups or companies that are also looking at this process?
To our knowledge, we are the only ones who want to develop a direct fuel cell with that fuel. We have looked into the literature, including the patent literature, and there's nothing. There's a company who does something relatively similar. It actually also uses the perhydrodibenzyl toluene as the fuel, but it first strips off hydrogen gas from that fuel and then uses that hydrogen gas in the fuel cell. So this is a two-step process in comparison to the one-step process that we want to accomplish. So accomplishing this in a one-step process has, besides the fact that it's only one step, also one other major advantage, which is that the hydrogen liberation step is requiring energy input, external energy input. And that reduces the overall fuel value of your fuel by approximately 30%. And besides, of course, you have to have a separate reactor in order to produce the hydrogen gas from the fuel first and then feed it into the fuel cell. So it's more complicated. There's more capital cost involved. And you want to save all that.
Well, this is very exciting. We really thank you for taking the time to share it with us. Bill, did you want to jump in?
I just had a question came to my mind, Kai. Yes, this is a fascinating subject. Have you been able to estimate, even at this early stage, what the relative upgrade costs would be for installing this in vehicles and or homes, just in terms of comparing to the existing EV cost? You know, the EVs cars are a little bit more expensive than traditional cars right now. And then heat pumps, you know, the cost of running a heat pump can be a little more expensive than our current natural gas systems. Do you have any feel for what it's going to cost when this is first rolled out, and then once it becomes, more volumized in a larger scale?
Well, again, the benchmark is conventional fuel cells. Okay, so overall, the capital cost of our fuel cell, assuming that we can make it so that it produces the correct power density, should be not more expensive than a conventional hydrogen fuel cell. It could actually be cheaper if you are factoring in the expense that you have for hydrogen storage. So you can buy hydrogen powered cars already on the market. But all these cars are relatively expensive because it's complicated to store the hydrogen gas in the high pressure cylinder. So you save all that cost. Okay, so the fuel cell itself should be in cost fairly comparable to a hydrogen-based fuel cell, assuming that you're not required to use more platinum in the fuel cell and all these things. So our primary benchmark is hydrogen fuel cells, and make a product which is less expensive and more convenient and safer to use than that.
And how about the cost to retrofit the gas stations and the delivery systems, the tank trucks and things like that? What's involved in setting up that whole infrastructure?
Well, there's not really any new infrastructure that you need to set up. So I'm pretty confident that you can use the tanker trucks just as they use them today, in order to just fill in a different liquor into them and just operate them the same way. And the same is true with the tanks at the gas station. Just pump out your diesel and fill in the HDPT, and that's it. The only difference may be that your pump stations would need to have basically two pumps, okay? Because you need to remove the spent fuel from the car first, and then pump new fuel into the car. And you would like to do this simultaneously. So your car, ideally your car would actually have two outlets to the tank. And then at the gas station, you would also have two hoses that feed into the car. One would remove the old fuel, and one would fill in the new fuel. So that's a difference. Then another modification is the number of the tanks that you need at the gas station, because you need one for the spent fuel and one of the new fuel. So the existing gas stations already have multiple tanks, because you have these different fuel grades, right? Each requiring a different tank. And then you have diesel as well. So you could repurpose one of the tank for the spent fuel and the other tank for the new fuel. Or if you want to use the space most efficiently, you retrofit the tanks at the gas station also with a diaphragm. Okay, and then the diaphragm moves as old fuel is filled into the tank and new fuel is moved from the tank into the car.
Thank you.
Bill, there's two other questions in the chat. Do we have time, or should we answer them offline?
No, I think we could go ahead and try those two. If people have to leave at 1, feel free, but we'll get you the recording afterwards.
Okay. Now Nancy's asking, a possibility kind of question. How long could it possibly take to get to commercial viability? Certainly that's a function of funding, but if you imagined you had infinite funds, you know, all the money that you needed, that you never had to wait for a next step, how long would you imagine?
Yeah, that's a good question. So, I mean, when the COVID vaccines were about to develop, people were very uncertain how long it takes. So conventionally, it apparently takes 5 to 10 years, right? And now that has been accomplished in 1 year because so much more resources flew into that. So typically technologies like that take approximately a decade to develop. So that's a rough estimate. So let's say a minimum of 5 years, maybe 7, 10 years, hopefully not longer than that.
No, that's okay. We are recording this, but we're not going to hold you to it. So it's okay. The last question is about the energy conversion process. And is it equally efficient across the different range of temperatures that you gave us in the environment? So for example, would it work as well in Florida as it would in northern New York?
Yes, because the liquid remains a liquid down to minus 30 degrees Celsius. So that's lower than 0 degree Fahrenheit. I tend to think in degrees Celsius. And it's has a very high boiling point, 300 degrees Celsius also. So it never boils. Okay, so the boiling point is way higher than the boiling point of liquid water. So basically, it remains a liquid in all climate zones. And with regard to the fuel cell temperature is fixed. And you need to bring the fuel cell to the operational temperature, no matter what the temperature in the environment is. And once the fuel cell is at that temperature, the waste heat generated from the fuel cell will keep it at that temperature. And if a few degrees difference in outside temperature don't really make a difference.
Okay, well, thank you.
Bill,
I think we're at time.
I think so. But Kai, thank you very much. This was a fascinating presentation and discussion, very hopeful. I think that your solution has some promise, and I'm hoping that you can get enough visibility that it is raised up to have priority and have some backing to get it actually implemented so we can see how quickly it can be rolled out. I'm going to stop the recording now. If people want to stay on for a few minutes to ask Kai any questions, feel free to unmute